Jenny, nice to meet you. I'm Sal.
All right, good evening, everyone. Make sure I'm unmuted here. Welcome. Normally we set up like 4 tables and then don't need that many seats. So this is the first time we set up not enough tables, so that's cool. Thank you all for being here. Actually, I'll turn this off real quick. As you can see, we got the whiteboard pulled out. So that's mostly what we'll be using tonight, but we will switch to some code towards the end. But my friend Clayton here is going to use the whiteboard to explain some stuff. Actually, should turn that back on. Sorry, I jumped the gun here. We're trying some new stuff tonight. If you've joined us online before, we used Microsoft Teams, and the experience was not great. So we're trying YouTube Live. Austin, would you mind changing the input to the PowerPoint for me? I think just 1 instead of 2. Yeah, sounds good. Well, I'm assuming you guys know what you're in for if you showed up at some random building at 6 o'clock on a Tuesday night. But tonight we're going to be doing some adventures in AI, talking about a little bit of an introduction to artificial intelligence. Tonight you'll notice there's 2 of us up here. So I'm Joseph Riddle, the organizer for the Spokane Python user group. This is Clayton. Clayton, you want to introduce yourself?
Sure. My name is Clayton Gravatt. I'm a data analyst here at Teletech, and I've been roped into talking about machine learning.
Sounds about right. Give that another shot. Well, try and get the slides up here in a second. But there's actually a few meetups that happen here in this building. If you haven't been to the other ones, there's the Spokane.net users group for all things .NET and C#. There's also the Spokane DevOps meetup for all things DevOps, like CI/CD, the cloud, all that sorts of good stuff. I don't know why this isn't working. Apologies. Come on. Well, that's all right.
You've got a flashing red light.
Yeah, yes we do. I don't know what flashy red light means. You know, I had it working and then I turned it off, and here we go. Oh, cool, green light, let's go. All the meetups that meet here in this building are sponsored by Teletech, the building you're in. Mark works here as well, Austin in the back, and I think we got Meg in the back as well, all work here. If you know anyone who's looking for a software engineering type role, or you yourself are looking, take a look at our website. We are actively hiring for multiple roles. Always looking for awesome people local to the Spokane area.
You guys looking for interns in school?
Yes, I believe so. Yeah, we are. Let's talk at the end if you're looking for that.
Yeah, cool.
Oh, thanks, Austin. Oh, there we go. Sweet. .NET user group is going to be meeting on March 8th. I believe that's about 3 Tuesdays from now. So they meet on the first Tuesday of every month at the same time and same place. Next month is going to be Mark presenting on, do you know what, Mark?
We're going to split abstract classes and interfaces and new stuff you can do with C#.
Abstract classes and interfaces and new stuff you can do with C#. Cool. Thanks, Mark. The next Python user group will be all things cloud, or all things hosting Python in the cloud. So we'll talk about using AWS, Azure, a couple other options for hosting your Python applications on the interwebs. The next DevOps user group is February 22nd. So that's actually next Tuesday. They meet on the 4th Tuesday of every month. And that will be a continuation of last month's Terraform discussion. And that will be hosted by Jenny Curry. Last name used to be Meadowcroft, but now she's married. Cool. Check out Intelitech on the social medias for more info. And as I mentioned, tonight it is Clayton and myself. So outline for tonight, like I said, Clayton's going to be going on the whiteboard to explain some stuff for AI, and then I'll hop back up here when he wraps up and do a little bit of a code demo and walk you guys through a code sample. And then that'll be it for the night. Hop into questions, have some discussion. Feel free to interrupt us both, especially me, with questions. And yeah, now that I finally got it turned on, I'll turn it back off. Otherwise, you'll just be seeing a video of him on the wall. Cool. All right.
Okay, thank you, Joseph. So before I get started, Python meetup. Who's used Python before? Great, that's a good start. And what about machine learning? Okay, cool. So last meetup, last month, I gave a general introduction to machine learning and talked through some of how you might go about implementing that in Python. But just as a refresher and to review, I figured we'll start with a little overview of machine learning again, talk about some of the branches of it, but the main focus for tonight is going to be on reinforcement learning. Hopefully we can get there. So start with supervised machine learning. Hopefully a lot of you have heard of it. This is probably the most broadly used kind of machine learning. But probably before I get into that, I should probably offer a definition of machine learning in general. It's just basically a method of teaching computers to do things without having to explicitly program a solution. Instead, we base our solution on data, and we let the computer look at the data to try and figure out our optimal answer, whatever that would be. So to start with, supervised machine learning. The example I used last time, sorry, was there a question? Oh, okay, sorry. I hate when teachers did that to me, like you'd move and someone would think you'd ask a question. Sorry. So supervised machine learning, an example to start with, last time I used housing data. An example problem might be, I have a set of houses of varying sizes, and I want to try and predict the price of the house based on its size. So if I have price on my y-axis and size on my x-axis, and I have a bunch of examples of houses, which I'll represent here with dots. So maybe smaller houses are worth less. And maybe in general, as houses get bigger, they seem to be worth more. A supervised approach to machine learning would involve a set of labeled data like these, where we know the price of the house and its size, and we try and fit a model to it. We try and figure out how to predict the price based on the size. And so an example of a linear model that we might fit through this data can just be represented with a line. Once we know how to fit our model through our data, we can start making predictions with it. Not too exciting, but that was our entire first talk. I guess I didn't need to spend an hour on it last time if I can do it in 10 minutes here. So that's supervised machine learning, regression specifically. In the case of housing prices, I'm working with continuous data. A house could be worth $1,000, $10,000, $100,000, and any number of cents. But the other main class of supervised machine learning would be something like classification. If I have a bunch of images that have dogs in some of them, cats in some of the other ones, labeled images, I can train a computer to be able to recognize those images and then generalize to predict new images. I feed new images into it and it tells me, is it a cat or is it a dog? Or maybe I'm doing classification of cats and dogs again, but based on other variables. Maybe one variable like weight. So maybe I have a weight on my x-axis, and then on the y-axis, this will be kind of weird looking, but I'll have dog and cat on my y-axis, and I might plot some data points here. So maybe I have some cats with a low weight, and maybe some dogs at a higher weight, and I could fit some model through this as well. A typical use might be logistic regression, where we fit something called a sigmoid curve through the data, where if it outputs a 0, it predicts it's a cat. If it outputs a 1, maybe it predicts it's a dog. And maybe there's some overlap in the middle where it doesn't do as good of a job. Maybe it has bigger cats. Maybe you have smaller dogs. So not a perfect model, but gets the job done. So that's the basic overview of supervised machine learning. Good so far? Good. Okay. Now, next section, unsupervised machine learning. This would be, I have no idea what the data points are. I just have a bunch of them. maybe with some arbitrary axes. Don't need to attach a label value to it, but the purpose here in a supervised machine learning algorithm such as clustering is just to look for patterns that exist in the data. I'm not looking for an answer necessarily. I don't need to predict if something is a dog or a cat. I just want to know what's there. And an example result might be clustering similar data points together, such as these. Here I might have 3 different clusters that it spits back out. And some applications of this might be something like fraud detection. You're looking at insurance claims and you want to know if something is fraudulent, or maybe bank transactions that are fraudulent. If something doesn't nicely fit within any of my clusters, it's maybe a little more suspect. And so that's something that can be given more attention to. Probably a little less used than supervised regression, but still pretty powerful. Supervised machine learning, sorry. But what about something like a game? Good example would be Tic Tac Toe. If I wanted to train a robot to be able to play Tic Tac Toe, or maybe more advanced usage would be drive a car, it doesn't nicely fit into any of our other design paradigms where I have labeled data and I try to get it to predict something. Or I'm not just looking for clusters that exist. I'm trying to get our agent or our computer to maximize some goal. For example, win a game, get better at tic-tac-toe. And the advantage of reinforcement machine learning applications is that I don't rely on labeled training data, and I don't actually need to know the why. I don't need to figure out, necessarily, the mathematical model underlying the data. So I don't need to know my cool line fit through the data so that I can generalize to new applications. All I care about is something that can play tic-tac-toe. And that simplifying nature of the problem allows us to do different things and apply different approaches. But before I can get into the actual application of it, we'll have to go through some vocabulary. Always fun. So to start with, I'm going to use the word state. By state, I just mean a snapshot of the current state of the environment, what things look like at a given time. For example, in a tic-tac-toe board, this could be one state. Or this could be another state. It's just what things are at a given moment in time. And this relates, the mathematical term would be Markov decision processes, where you have discrete time steps and transition states that move between them. But more simply, it's just a tic-tac-toe board. But I can represent the current state of my tic-tac-toe board with some hash or variable that describes it. So just for simplicity, I'm going to label each of my spots on the board. I could say this is cell 1, cell 2, 3. Hopefully you can see the pattern. 6, 7, 8, 9. And so if I wanted to capture a snapshot of this board, for example, I could do so with just 9 variables. So in cell 1, it's empty. Use E for empty. I could use a 0, but it looks a lot like an O. Instead, I'll use an E. E for empty. Spot 2 is also empty. Spot 3 has an O. So on. Empty. 5 has an X. Oh, whoop, already lost my pattern. E, 7, 8, 9, all E's. Okay, so that's a state. That's all I mean by state, is just a current representation of my environment, which in this case is a tic-tac-toe board. And the next piece of vocabulary is action. An action, in this case, is just a move made by my agent or my robot or my reinforcement model trying to do something. In this case, it's just putting a token on the board. Hopefully pretty simple. And the last piece of vocabulary is reward. The reward is what I'm going to use to incentivize my agent to keep doing good things and not do bad things. So every time it wins tic-tac-toe, I'll give it a cookie. Something simple as that. So now that we have those pieces, now comes the lengthy drawing bit. Guess I didn't need to erase my board. So instead of a nice mathematical function or some cool sigmoid curve or a linear model, I'm just going to make a table. And this is called a QTable, where the Q stands for quality. And it's just going to be a representation of the reward that my agent expects to get from choosing a certain action in a certain state. And I'll show you what I mean by that. So to start with, this current state of the board I could capture, and I won't write out all the E's, but my first empty board state, there are 9 actions that I could take to start with for the first player. And I'll define that as just putting a token at one of the 9 spots on the board. Actually, that's probably a little too small. Arduous. Okay, lots of drawing. So first time my agent plays the game. He has no idea what's going on. So he has no idea what to expect any action to take. He could put it anywhere, doesn't know what to expect from it. So to start with, I'm going to assume that each possible action he could take has a starting Q value of 0, just a good starting point, good neutral starting point. So when my agent goes to make his first move, he has no idea what to start with, and so he'll just pick something. And when you use NumPy, and you take the argmax of an array, or find the maximum value in an array, and it's all zeros, it'll just give you the first one, so that's what I'll mimic here. So my first move that my agent is going to make is just going to be in the first spot, and he'll be X. Now, you need someone to play against. So, who would like to volunteer? Yeah. Oh, you want to start with, what was your name again? AJ? Top middle? Okay, thank you. So, top middle was AJ's move. Very good. So, we're going to capture this state. So, we have an X. Thank you, that's very convenient. We have an O, and then 7 empties. So he made that move. How'd he do? Doesn't know yet. Again, doesn't know what to expect in this situation. So once again, it's zeros. Okay, so again, he doesn't know what to do. So maybe he just takes another random spot. For convenience, I'm going to put him in the middle. And then you guys are probably too good at Tic Tac Toe to illustrate my example. So I'm going to say he's playing against a random component that's also not very good. And that random opponent goes here. So we have a new state. Another arduous drawing. So XO. And yet again, no idea what to do. This is first time looking at the environment, and so all zeros, he makes a move. And lucky him, perfect to illustrate my example. How lucky is that? He happens to win. Cool. So just to mark what actions he took. 5 and 9. Okay, so my agent, very luckily in the first example, so I didn't have to draw it multiple times, won his first game, and I want to encourage that behavior. So I am going to give him 1 cookie, and I'm going to tell him, okay, this move that you just made, given the previous state, when you put that X right here, that was a fantastic move. You earned a cookie. So I'm going to give him 1 point over there. Now, the problem is, I only gave him a point for that last move, the move that won him the game. This doesn't help him at all learn how to get from the first move to that last move. And so to encourage the behavior, I am going to give him some points going backwards as well for those previous moves he made. Not because they won him the game, but because they brought him closer to winning the game. And because he didn't win off of it, I'm not going to give him the full point, I'm just going to give him part of the point. So I'll decay it by a little bit. So maybe I'll multiply it by 0.9 at each step going backwards. Quick math. Okay, so.
Can I ask a question?
Please.
So is that art or science, assigning those decaying values, the rate at which it decays?
Art or science?
I
Oh.
mean, like how did you come up with those values?
Oh, excellent question. So the decay factor, so there's a lot of research out there, and the general consensus I've seen is that values should be somewhere between 0.8 and 0.99, but it depends on your individual application, and I would recommend trying it. So both, I guess, but trying a bunch of different ones is one of the what's called hyperparameters you can change about model tuning itself, where it's not a parameter of the model, but rather something that lives above it that teaches or that describes how the model should be trained. Excellent question, though. Okay, so we have our distribution of cookies. We'll play again. I'm sure this is very exciting. I actually got a lot of really good feedback after my last presentation. I made this PowerPoint, and people gave me fantastic feedback of how to improve it, and I've decided to absolutely ignore it and just scribble on the whiteboard instead. Maybe on the next one I'll find a middle ground. But let's start over with our fantastic little bot now that knows how to play games. So what is the first move that he's going to make? When we start over, what's our state right now? We're all empty, and I'm very lazy, and I didn't write out the whole thing, but it's this first column. Does anyone want to venture a guess as to what move our agent is going to make? What spot is he going to go into? AJ? 9. Close. So the method that our little agent is going to use to determine what move he should make is just a greedy policy where he maximizes his reward for the next move he makes. Basically, he's just going to figure out which number in his little quality table is the highest. So to start with, our highest expected reward, our highest quality value in our empty state is just 1. So the first move he's going to make is just 1. So this is where he's going to start. Now, the problem with this is probably better illustrated outside of Tic Tac Toe. So we're going to pause the Tic Tac Toe board for a second. I'm going to hop over somewhere else. Let's say I had a series of squares to stand on and some starting point. I'm teaching him to play some game. I don't know what this is, but here's my starting point. Our agent starts here. So I'll give him a little X. And then there's an associated reward with getting to one of these end tiles. Maybe this is a lizard, and he wants to eat a bug. And right here, there's 1 bug. But over here, there's 10 bugs. And as a lizard, he likes bugs. So his goal should be to eat as many bugs as possible. Now, to start with, again, he doesn't know what to do. Imagine we have our empty QTable again, and he randomly decides, okay, I'm gonna go left. And let's say when he gets to the edge of the board, it ends the game, he's full, he's done, he stops to relax. So our first move that our lizard makes brings him over here. And then he's done, then he stops. And our associated QTable with that might look like, okay, so he turned left, and he got 1 point from it. When he goes to play it the next time, let's say he didn't make that move, all he knows is that going left gives him a point, and that's the best thing he's ever seen. So he's just going to keep going left, and he's never going to try going this way, because the associated value with this is unknown, and to start with, it's 0. Even if he did go this way once and then back a couple times, all he knows is that going right means 0, and he doesn't like 0. So he's going to get stuck in this local optimum of 1 point. And so we have to change his behavior to take advantage of what's known as exploration versus exploitation. There's a balance we have to get. So if he gets stuck just doing what he knows and trying to get better at it, he may miss things in the grand scheme that are better, that in the short term don't look as good. So instead of letting him make the decision all the time and potentially getting stuck, we use another variable where we randomly decide. Sometimes you don't get to pick. Sometimes I'm going to pick for you. I'm going to force you to go to another spot so that you have to learn. You have to see other points in your environment. So maybe instead of just following our QTable, maybe there's a 25% chance he gets a random reward chosen for him. But he still gets to observe it. So maybe in this time he starts here. And so now we have a different state to start with, and O goes up there, and the same process continues out. Until eventually we have our QTable updated with however many hundreds of different combinations there are, and assigned Q values with each of those that tell our agent the best route to get through. Okay, I feel like I sped through that ending bit. Any questions so far? Yeah, AJ. What would we do if he lost? That's a fantastic question. So, just like we can give cookies, we can take them away too. We're not the benevolent ruler of this bot. So, let's say he lost. And I won't go through, well, not exactly valid. I don't know how he managed to lose that fast, but let's say he did lose. What we could do is, similar to giving him a cookie in a certain spot, we could take a cookie away. Let's say for some reason he managed to lose this one. Maybe he made the wrong move. That one gets a -1. And similarly, it propagates back. And again, this is not the actual state table. I just don't want to draw another 6 of these rows. So maybe his prior moves were also bad. And they get a -0.9 and a -0.81. And similarly, well, I guess that doesn't make sense. That's still a positive one. We'll put -0.81 over there. And maybe we update it by just a portion of that each time. Maybe to start with, it's the full 0.9 that gets decayed back. But maybe over time, as our agent gets better and explores more of his environment and we're more certain that he knows how to make good decisions, maybe we give him less points. So that initially he learns a bunch and then maybe he slows down his learning at the end to fine-tune it. There's all sorts of different ways we can adjust the behavior just by changing some of the parameters of the model. Question?
Yeah.
Yeah.
For the exploration part,
Yeah.
are we giving the agent a permanent reward, like random reward, or is it just like for that? Like, are we giving it a random action or a random reward?
Oh, so good question. It's a random action.
Okay.
Cool. I didn't repeat the question. Are we giving a random reward or a random action? The answer was we give him a random action that forces him to explore his environment. We don't want to randomly reward the wrong behavior. We don't want to give him a point if he loses, but we do want to make him try other things.
Push him off the path.
Exactly, push him off the path. That's the exact idea. Or like you have a robotic dog and you kick it to see if it'll fall over or not. Cool. Well, that's most of what I had. Went through faster than I thought. Any other questions? Yeah.
So, I mean, is this the basic premise behind stuff like AlphaGo?
Is this the basic premise behind stuff like AlphaGo?
I'm not sure if you're familiar with it.
No. Can you give me a summary of AlphaGo?
I mean, are you familiar with the board game Go?
Yes. Oh,
So
yes.
it was Google's like AI group
Mhm.
that developed the first software that could play at the professional level.
Okay.
And it was machine learning.
Mhm.
So, I mean, is this pretty much anytime you're dealing with a game, is this the basis for,
Okay.
is there other kind of like machine learning
That's
like that, or is it just reinforcement?
a great question. So the question is AlphaGo, Google, right? I'm getting lost up here. Google's agent that could play Go at a professional level. Is this all that reinforcement learning is? Or is there more to it? Or are there other things that it could be? And this, as an example, is just one example that falls under the broad bucket that is reinforcement learning. There are other approaches to it. In this, it's model-free, and I'm not trying to approximate the mathematical function that goes underneath it. Other models do it differently. Something like dynamic programming, where you know the underlying factors of the decision process of the environment, and you just try and search them. A totally other thing. But interestingly, on AlphaGo, now that you described it to me, I know a little bit about it. there was an interesting problem with it where the number of combinations you have is really big. So you can't necessarily populate the entirety of QTable with it. And so instead, their approach, I believe they took, was they found a way to generally evaluate the board at a given state. And I don't know how to play Go, so I don't really know how best to describe it to you. But as great question. So as a basic understanding, there's a board, and there's a bunch of spaces on it, and there's one player gets a black chip and one player gets a white chip, and the goal is to get as many chips that are your same color, something to that effect. I'm sure there's something more to it, but the general approach that they took to it, I'm representing the two of them with X's and O's instead, because I don't have a white marker that can go on the whiteboard, unfortunately, was they figured out some way of generally evaluating the board at a given point. Because the win of the game was so far out in the future, there were so many moves out, it was hard to predict all the different paths that it could take. So instead of distributing the cookie at the point that it won, they had some way of evaluating, okay, at this point, X, or black or white, is further ahead. So 10 moves out in the future, X is winning in this scenario. And so they'd give some points for it at this point. And they'd slowly build up to that instead. I believe it's similar with chess. There's some way of evaluating maybe the number of pieces that each person has lost, and I'm sure there's more nuances to it, but that's my general vague understanding.
19 by 19. So just the number of
Yes,
combinations is
19 by 19. There's a lot that could happen. Cool, almost had an answer there. Any other cool questions? Great. Well, I've bored you for long enough. Joseph, would you like to show the actual Python for it for the Python meetup? Cool.
So we're going to write out all of the code for how to, no, I'm just kidding. We're not going to write out all the code on the whiteboard. That'd be terrible. I'll just leave that. What we are going to do is hop on the computer, like I mentioned before. Oh, first time, let's go. And I'm going to walk you guys through, and we're going to take a look at an example using Python and the NumPy library that generates an agent to play Tic Tac Toe. Yeah, I think you're good. Yeah, yeah. I mean, we can hang out up here.
Watch from the sidelines.
All right. Sweet. Give that just a second to warm up or whatever it does. So the code I show here today isn't available yet on our website, but it will be after the talk as soon as I push it up. We do have a website, SpokanePython.com. Hopefully that's not too hard to remember, where we have a list of all the previous talks that we've done, at least since I started organizing it. It also links to a GitHub repository with some of the code for talks that go back several years, and that's where we upload our code samples to when we have them. Can you guys see that okay? Do we want to dim the front? No.
Do you guys record it and upload the video from the?
Yeah, so the video is actually live on YouTube right now. So say hi to the online people. And we do, so it does get recorded. The video will be available on YouTube. We link to the recordings on the website as well as the meetup page as well. I think that's probably where you all signed up, was on meetup. Cool. So let me just close some stuff out. How many of you, Clayton asked this earlier, but how many of you have used Python in some capacity? All of you? Okay, perfect. How many of you have used Python at like a professional level? Okay, cool.
Used to have work, but
Hey, that counts. If someone paid you $1 to use it, you throw professional Python on that resume.
Professional on my resume.
Perfect, perfect. Cool, so let's just close this all. We'll just start with that. We'll look at a README. So this code sample is actually forked from another code sample online, and then I just made some changes to it to make it the way I wanted it to be, the way I wanted it to work. Tried to add some comments and stuff and kind of reorganize it in a structure that felt easier to understand. So first thing, let's do, we have 3 main files, and I'll just explain the project structure really quick for those of you who are new to Python or aren't familiar, though I think everyone was familiar. In Python, generally we'll have a top-level package in our folder or our source repository. In this case, it's just named Tic Tac Toe. A couple files we'll have inside of there include, can you guys see the left side of that okay? I can try and tuck this back a little. We'll have a couple files including dunder init.py. If you're not familiar with what dunder means, it's just short for double underscores. Very common I guess slang in the Python world because it uses double underscores for many things. Dunder main is the entry point for our package if we do like python-m and then the name of the package. So in this case, Python, and I can just show you here, python-m, let me turn my keyboard on, Tic Tac Toe, we'll run it. In this case, it's not doing anything because we didn't give it a command. And then, so those are just kind of basic Python files that you'll find in almost any project. And then the more interesting stuff is we're going to have our board module, our game module, and our players module. Oftentimes in Python, you'll see people include everything in just one big module, especially when you're looking at data science type stuff. It's just kind of one long top to bottom approach, and that's kind of how this code sample was when I first took a look at it, and I just tried to break it up to make it a little bit easier to understand and reason about, maybe even unit test if we wanted to go that far. So let's start with the board here. You can see a couple things at the top. We're importing NumPy, so that's the only requirement to run this code sample as specified in our requirements.txt. And I will include instructions in the README on how to like get the project running, which is really just going to be a pip install requirements, and then you should be pretty much good to go. So we are following kind of an object-oriented approach. Pretty much all our stuff is defined in a class and methods within the class, FYI. So here we'll define a board. Our Tic Tac Toe is virtually always a 3x3 board. There might be versions of it where you have a bigger board. So we'll just allow for that here. We have a rows and columns parameter or argument. And then inside our initialization or init function for the board, we're just going to create an internal reference to our board. In this case, we're going to use NumPy ND-array data structure, which is, if you haven't used it, basically in many ways similar to the built-in list in Python. In this case, we're just using NumPy to make a couple things easier. For example, this numpy.zeros just creates a 2-dimensional array in this case, and it just pre-populates all of the values with zeros. I won't belabor every specific function because some of them aren't too interesting. In this case, we are defining our own dunder string function. So what this does is just prints the board out for us. So let's actually go ahead and create a board, and I'll just show you guys. From Tic Tac Toe. Import board, and we'll just do board equals, oh, oops. Yeah. From board equals, a lot of boards on the screen. In this case, let's do like a 2x2. And then if we do print board, you can see we have our nice little 2x2 board. In this case, the print function is kind of assuming it's a 2x2, so it doesn't work super well on the or it's assuming it's a 3x3, so it's not working super well for the 2x2, but you get the point. A couple other just kind of boilerplate functions. We have a reset function on our board that basically just takes to an empty board. We have copy, which just returns a copy of the board. We can get the position or the value at the position of a board. So if we were to pass into this function, well, I guess I can just show you again. Board.get, and then we'll give it a tuple, 1, 1, and you can see we have nothing there. Same thing set, so we can update the position of a board. And then here we have a larger function that's calculating who the winner is. So if all of the spaces on our board are full, we're looking through to see if there's any like win conditions for either side, or if it's I think a cat's game is what it's called when no one wins. So in this case, we're just looking through the rows and the columns to see if there's 3 in a row, the diagonals, checking for a tie, etc. And then the final bit is just listing the available positions still on the board, so places where someone hasn't played already. So nothing super interesting, nothing really to do with AI at this point. We'll look at the players next. So in this case, we're actually using something, and I'll kind of segue away from AI just for a second. Hopefully that's still viewable online. So in this case, we're defining 2 different types of players. We have a computer player, which is going to be like the AI that we're training, and then we're going to have a human player, which will just take input from the standard in or the console. But something that we're doing that if you haven't used relatively newer versions of Python 3, you might not be super familiar with, is a protocol. So if you've used Java or C# or other object-oriented languages, you're probably familiar with what an interface is. And in Python, a protocol is very similar. I've talked about this, I think, in a previous talk, so I won't go too in-depth on it. But basically, it just allows us to use type hints and take advantage of like full Python 3 type hinting, but still have one abstraction for both of our computer player and our human player. And so basically what we're doing here is defining all of the methods or functions that we would expect to find on a player, whether it's a computer or a human player. So in this case, we have a function that's going to take in a list of available positions, a current board, who the current player is, and return the chosen spot to play, as well as some other kind of boilerplate functions. So here's where we'll start getting into a little bit more interesting stuff that Clayton mentioned. Here we can see LR, which stands for the learning rate, so how quickly our AI is going to kind of try new spots on the board or try new ways of playing, as well as the decay gamma, so that is, I believe, has to do with the backflow, is what Clayton mentioned. So basically, if the AI wins a game, how much it decays. So we went from 1 to 0.9 to 0.81, and so the decay gamma is going to calculate how much that number decays as it goes backwards. Am I on the right track, Clayton?
Yeah, good so far. So the learning rate is how much the key values get updated in new learning scenarios. The decay gamma.
Cool. Awesome. Cool, thank you. So here we're looking at the function for the computer and how it's going to choose the next move. So we'll do one of 2 things. We'll either choose a random move, like Clayton mentioned on the whiteboard, specifically with the, I believe it was a snake and a mouse, or the animal eating the other animal. I forgot exactly what it was. But, sorry? The lizard, right, yeah. So the lizard can get stuck always going left and gets stuck in kind of this local optima where it only just wants to keep doing the same thing over and over because it knows it leads to something good or a reward, and it won't ever try and go right in his example because that's an unknown and that's, you know, new and scary. If it knows it can always go left, it'll just keep doing that. And so this code, this section here is basically taking that into account. We're just generating a random number between 0 and 1. And we're checking to see if that number falls underneath our EXP rate. What does the EXP stand for?
Explore.
Explore rate, right, thank you. So if our explore rate is, say, 0.5, and we pop out a random number that's 0.25, then our AI will decide, or our agent will decide to just pick a random move. And that's how we're kind of forcing it to explore different ways of playing Tic Tac Toe that it hasn't already tried, not get stuck in a local optima. I think, generally speaking, that decreases the more you train your AI or your agent, right?
It can.
Cool. In the case that it doesn't just choose a random move, it's basically going through and looking at what it knows, all of its previous moves that it's played, and looking to find the one with the highest value. So basically, actually, I won't use the whiteboard because we already moved it. But if we had say moves with something like move like 1, 2, 3, or no, that's not a good example. Move 1, 1, move 2, 2, and move 0, 0, all being coordinates on the board. And then that gave us a score of, like, say 10, so it was a good score. And then if we had 1, 1, oh, that's all right. 1, 1, 2, 2, and then like 3, 1. So basically, in one move, it has a diagonal and it wins, and the other move, it doesn't give us anything. That might be 0 or even a negative number, as Clayton mentioned earlier. So basically, all it's doing here is taking the maximum value of all of our different moves that we've tried already. In that case, the computer decides the move that it's going to do and makes that move. And then here is our feed reward function. So as the method doc says at the end of the game, we're going to back propagate and update our states value, basically update our object that keeps track of what moves we did and how well they worked for us, what kind of rewards we got. Clayton, you want to touch base on this function?
Not really, but so that's just updating the Q value at a given point based on whatever reward it got because it decayed going back.
Awesome, thank you. Cool. So let me delete this. Let's actually train this thing now before I go to the next module and bore you all to death. In this case, in this code, we have since we're using VS Code, we have a launch.json where we're just defining basically the ways we can run the module inside of VS Code or run our project inside of VS Code. So let's run train, press play. And you can see here we're puking out way too much information. But basically what's happening here is the computer, computer 1 is playing computer 2. And I'll show you what that code actually looks like. So if we run our package and tell it, hey, train my agent, or my AI agent, basically what we're going to do is create one computer player, another computer player, and then we're just going to tell them to play, in this case, 5,000 games against each other. And then we're going to save basically our collection of all the different possible moves and how well those worked for us. In that case, it's pickling that and saving it to this file. Pickling, if you're not familiar, is kind of I think it's a Python specific. It might be used in other places, but I've only used it in Python. Basically just a way of storing data in a binary encoded fashion. Actually, generally wouldn't recommend using it. It is not very secure, and there's a ton of security vulnerabilities with it, but in this case, we're just kind of using it to save some data to the disk, so we're not doing anything too crazy. But in this case, we've created this new policy computer, which is a list of all the moves and how well they work for us, and we've saved that file. And so now, if we go ahead and play our game, in this case, I can just run it from the command line. Tic Tac Toe, play. We can see our computer takes the first move, and it chooses to go in the bottom right. And if I go in the middle, it's going to go on the bottom. So it's already, we can see that it seems to understand, either it just made a random move or it seems to understand that it should try and make multiple x's in a row. So if we do 2, 0. So now it's, okay, we thwarted its effort from going across the bottom of the board. Oh, sorry, I guess you guys can't see that super well. So now it's trying to go up vertically, as you can all see, and we actually can win it right here, so we'll do that. Row 1, column 2, oh, whoops. Row 0, column 2, and we've won the game. But let's actually train the computer, I don't know, like once, and see how good it is. So if we delete that, basically our file that's a list of like, that the agent is using, and we rerun our train, then it trains on one game, and so now our super fancy agent that has all of one Tic Tac Toe's game worth of experience, we'll see how well it does or how it moves. So again, goes in the bottom right, and let's go in the middle, and it's going across the bottom. 0, 2, oh, whoops. It won. I had to leave the wrong file. It's just doing the same thing over and over. My example is falling through. Let's go 1, 1. Whoops, there we go. 2, 0. Okay, so clearly I did something wrong because oh, there we go. It had the chance to win, and instead, it just made this random move. So we can see it's not super smart at this point with just one game, though I am surprised that it seems to just keep doing these same moves over and over, especially after it's only trained on one game.
Is it just starting at the bottom right, moving across like this?
It might be. I mean, so you had mentioned in your example, specifically with NumPy, that it'll just grab the first value it can. So it might just be an implementation detail where it's just happening to grab the last available spot and then just move backwards until it can't find a spot anymore. Which makes me curious if when it won that game earlier, if it was actually doing anything smart. Here, I'll just kill this. So I believe the values that the number of games we were actually trained it on was something like 50,000 games. And that takes not a crazy amount of time, probably like a couple minutes. So what I can do is kind of kick that off since I've deleted the file, and we can run that. And if anyone wants to have a go at trying to beat the super fancy AI Tic Tac Toe after it wraps up, then we can do that. I'll just let this go in the background. Yeah, I think that's about it. There's one more module that I didn't go over, which is basically just the game state. I think the most interesting stuff is in the computer player. The game module is basically just keeping track of our board state, our players, whose turn it is, giving a reward to the player that makes a better move. In the case of our human player, we actually have most of these functions are just not doing anything. So that way we didn't have to write any specific logic for the computer versus the human player. If we pass it a human player, it'll just call this feed reward function and it just won't actually do anything. Yeah.
So in Tic Tac Toe, I think there's only like 8 winning boards. How would you improve the algorithm to take into consideration 8 winning boards?
So the question was, there's only about 8 winning boards in Tic Tac Toe. How would you improve the agent or the algorithm to take that knowledge into account? That's a good question. Clayton, hit me with it. Well, I mean, you could write some Python code. So one conversation we were having.
I mean, I think what I'm saying is there's only 8 ways you can have 3 in a row for each bit.
Yeah. So that's.
So that's a huge number that we can reduce how many considerations we have to look at them.
Right. And I forget the exact terminology, and I think there is another game that uses this idea, but I think we can take advantage of the fact that, like, if you have, say, I'll just draw it on the whiteboard real quick. Like, if we have this, it's like functionally equivalent to this. Like, that's basically just a reflection or rotation of the board. And
similarly, the 0, 0 with next to the middle is equivalent to what you have there as well.
right.
So like there's just a whole bunch of ways that we don't need to consider to be done on. And I would actually,
So you're saying that is
it's exactly the same.
right.
But for actually winning positions where we give a 1, there's only 8 positions we can win for each column.
Mm-hmm. Yeah, that's a good point. As far as how to implement that, I'm sure there's a way, probably several ways.
Really asking is, if you know that the limitation in what's possible, like Go, there's no limitation. Pretty large. There's a lot of things that we can say, it's not there, we can not do it.
Yeah.
Only position. But it's not.
Yeah. Yeah, that's a good question. I'm not sure exactly what techniques you would use to do that, though. See, this thing's still going. Let's see.
If you look at each board as being bit map, then you can look at whether you look at the bit map already and just make that.
Looked at the what already?
You can map it into 9 bits, 0s and 1s. 1 for each bit is actually two 9-bit numbers, and you can then eliminate a whole bunch of options. Just as a thing.
Yeah. Did you guys catch that? Okay, cool. I'm having trouble hearing through the mask. I'm having trouble hearing through the mask.
Okay, so if you look at how to represent every single Tic Tac Toe board, it's essentially 2 9-bit numbers, where 9 bits is just 0, 1 for each bit. It's 2 9-bit numbers, which is fairly small in terms of the number of possibilities. And so as soon as you started to look at an option, you only have to look at, that, whatever 9 bits is, what's that, 2 to 9. Like, that's the total number of options you could possibly have to examine to get all the possible scenarios that you could possibly have. And that would reduce how many possibilities you can look at across the entire range.
Yeah, that's a good point. I mean, we might be able to train this thing at what that took, like 2 or 3 minutes, few minutes. But yeah, might make it train significantly faster. Let's see. Okay, so we finished training on 50,000 games instead of 1 or just a couple hundred, I think is what we were doing before. So if we play it, anyone, AJ, anyone else want to hop up here and try playing it? You want to? All right, let's go. You want to hop up? Here, I'll throw my mask on for you. Oh, nice. All right. Let's see how you do. It's all yours. Are you okay being on the video? Or is your mom okay with you? Okay, good. Good thing your mom's here. Ooh, well played. So we might have a bug or something. It seems like the board or the AI is just playing the same moves over and over, which is less than impressive. Let's try and take its. Yeah. Let's do, so 1. Nope, I keep getting the columns. Sorry?
It's a solved game. It actually is playing the ideal movements.
Is it? Oh, I don't know much about it. Do you want to expand on that? Or?
So, Tic Tac Toe, if you play it a certain way, you will always win as the first player.
Really?
And it's not playing the ideal move, starting move. Our ideal starting move is playing in the center.
Yeah, it doesn't seem like
So
it's.
it can either force a
Gotcha.
Doesn't play the ideal.
right. It's not. Its first move is not ideal. Its second and third move are ideal.
What is
Really though, because I mean, it didn't even attempt to block.
Yeah, it is.
Stop.
So you're saying the optimal move would be played center.
This is a training set that can be evaluated no matter how well it's doing, because it is possible to look at what
Yeah, it doesn't seem very smart. I think our AI might be a little broken. I will try and fix that or take a look at that before I upload it. That is a good point, though, that if AI or if Tic Tac Toe is a solved game, we might be able to take advantage of that when we're training it to, I don't know, I'm not sure exactly how, but. Sorry? Yeah, it's always win. Yeah, I think it's always win.
It's to always tie.
But never, so it can never, it would basically, if it was playing the perfect game and always going first, it would never lose. It could either win or a cat's game. Yeah. Yeah, one limitation too, other than the fact that it doesn't seem to actually be playing very well, is other than that very large hole, is that we're, I believe, only saving the moves currently for the player that always goes first. So if we were to, say this was actually doing well, and we were to switch it so we went first and the AI played second, we might see it not performing as well, because in this case we just saved the like the move set of the first one, and that one always goes first. So there's a little bit of refactoring to be done there, other than the fact that it's not even playing very well. But if we got it to play well and kind of we're looking at ways to improve this, that would be probably the next step. AJ.
So you could always predict what move it would go to, because it always goes in the react position. If you go leave it in the spot 1, 2, 3, 4, 5, 6, 7, 8, 9, it will go in the greatest possible spot. It's supposed to go in 9. But if I was to go in 5 in the middle, it would go to 8. And if I was to run off 7, it would go up to 6.
Right. Yeah, no, that's a great point. It's, the way it's playing now is, I mean, we could probably take advantage of that to always beat it, since it's just always going in the same, basically, like you're saying, like most significant spot to least significant, or from 9 to 0. Yeah, that's a good observation.
This one have the
So when it's,
example, the Tic table, 25%, you just said, hey, 25% randomness. Does this have that in there? What's that called? Epsilon?
so when we're, where is it? When we're training it, it'll take into, so basically we're passing in this, this EXP rate, or Explorer rate. And when we're training it, I think we set that to some relatively lowish number, or it has a default. So we're defaulting that to 0.3. And so when we're training it, there's like a around 1 in 3 chance that it will make a random move. But then when we're actually playing against it, we change that to be 0. So we'll always attempt to choose the best move when it's actually, I guess if you have like train test mode, in the test mode, it'll just pick what it thinks is best, and it won't have like the random move. Yeah. Cool, that's about all I got. Bummer that this isn't working very well. I will see if I can figure out what's going on with it when I upload the code. And that will be available probably later tonight or tomorrow. Yes, SpokanePython.com is the website to check out if you want to go look at the code or watch the recording back, as well as our YouTube channel. Any other questions, Clayton?
So would you recommend against refactoring code 15 minutes before this?
No, not at all. Yeah, no apologies. Yeah, not quite as prepared as I generally try to be. Just, yeah, some other stuff going on. But I would not recommend that. Yeah, not taking someone else's code and basically taking a Sawzall to it and just chopping it up. But it does look nicer, and it's it got a couple modules. As far as it looks nice. Yeah, it doesn't. The performance is, you know, whatever. But it looks nice. Yeah. No, that's a great point. That's I believe so. I believe so. Yeah. Cool. Well, thank you guys. Thanks for coming. Thank you, Clayton. Yeah, feel free to hang around, chat a little bit. If you do have suggestions or for future topics, like I said, next month is going to be hosting Python in the cloud. And that one will actually have another Intel Tech employee, Reese, will be up here with me. I think he has several AWS certifications, so this should be a good one. Yeah, if you have suggestions, toss my way. Otherwise, feel free to hang around and chat. You want to talk about internships, so we can do that. But thank you, everyone.